Okay, so we're going to be talking about formal charges and resonance. Originally, this was part of the previous video when we talked about Lewis structures. Then I thought maybe that's not a good idea because I want the students to make sure that they understand Lewis structures right. And if I add more material, they're going to spend less time working on the Lewis structures. So I split into two separate videos. This second video is going to be shorter, but I think it will help you more to split as two different videos. Okay? Remember when we was doing Lewis structures that sometimes we come up with more than one answer. Look at the nitrite ion. If you do the Lewis structure, and I'm not going to put the brackets for simplicity, I'm doing it on purpose, okay? But remember, it looks pretty much like this. We did one similar to this one. So when we see that nitrogen does not fulfill the octet, we're going to borrow a lone pair from one of the oxygens. And the question was, which oxygen? Well, I can borrow from this oxygen, and I come up with this molecule in here, with a double bond to the left, or I can borrow from this oxygen, and that gives me this other molecule in there. Now, in this particular case, they're really the same molecule, but they're the same molecule because the two oxygen atoms are the same, but sometimes they're different, okay? So you follow the rules, and you end up with 2 or 3 answers to Lewis structures. That's correct, okay? If you follow the rules, you're fine. This is what I tell my students, read the question. If I ask you, what is the Lewis structure of the nitrite ion? Either answer is correct. If I ask you, what are all of the Lewis structures of the nitrite ion, then that means I want all of them, both of them. And I can ask you which one is the most important. And we are going to cover that, okay? So this is very important in chemistry. Read the questions. Answer what the question is asking, okay? Take your time, it's worth it. So whenever you have 2 or more answers to a Lewis structure, we call that resonance, okay? That means, like I said, they give you a definition in there, but basically it's just the answer to solving the Lewis structures, okay? Every form that you come up with, we call it a resonance form. They separate them with a double-headed arrow to indicate the resonance forms. Go back in there. You can see the double-headed arrow to indicate that these are resonance forms in there. But what you have is not one or the other. You don't even have a molecule that keeps changing. Sometimes on the one on the left, sometimes on the one on the right, and it keeps changing back and forth. No. What you actually have is a hybrid. It's called a resonance hybrid. Just like if you look at a Labradoodle, it's not a Labrador, it's not a poodle, it's somewhere in between. It has some characteristics of one, some of the other. So the resonance forms hybridize to give you the actual structure of the molecule. Now, in the case that I gave you before, both forms are equally important, but when the two atoms are different, some form is going to be more stable than the other one, which means it's going to contribute more. So they will ask you that different ways. They can ask you who is the most stable, who is the most important, who is the most likely. They're asking you for the same thing. Which one contributes more to their resonance hybrid? And to answer that question, we need to study formal charges. Not difficult, I promise. A formal charge is a hypothetical number, meaning there's not a physical meaning attached to it. You're going to see that in chemistry, okay? Sometimes to solve something, someone comes up with a number, and there's a set of rules on how to calculate that number, but if you use that number, you can compare. We're going to see here how formal charges will allow us to see which of several resonance forms is more stable. Later on, like when you're doing redox equations, you're going to be looking at oxidation numbers to see which atom gets oxidized, which atom gets reduced. There's a bunch of times when you use hypothetical numbers. Okay? I call it hypothetical because it says that would be the charge the atom would have if we could redistribute the electrons, blah, blah, blah. The fact is we can't. Okay? So I don't care about the definition. I just care about calculating the form of charges and using them. Because if you calculate them correctly, you can use them, even though it's a hypothetical number. So how do you calculate form of charges? It's the number of valence electrons minus the number of lone pair electrons minus half of the bonding electrons. This formula, you need to know it. I don't give it to my students, then to be able to use it. One way you can tell that you're right is that when you add the formal charges of every atom in a molecule, they need to equal the charge of the molecule, which of course is going to be 0 for a neutron molecule, or the charge of the ion. Notice that we talk about the charges of each atom. If you have a molecule that has, let's say, glucose, C6H12O6, I want the formal charges of the carbon, the formal charges of the hydrogen, the formal charges of the oxygen. That's the only way I can compare. Some students calculate the formal charges of 1 or 2 of the atoms. Why? Or some calculate the formal charges for the molecule, which ends up usually being a mess. No, calculate formal charges for each individual atom. Okay? So let's do some examples. Carbon monoxide. Okay, so we talk about valence electrons, lone pair electrons, and half of the bonding electrons. So carbon has how many? 4 valence electrons. Oxygen has 6. Lone pair electrons, 2. Remember, we subtract these numbers. Lone pair electrons for oxygen, 2. Half of the bonding electrons. The bonding electrons for carbon is 2, 4, 6, so half is 3. For oxygen, it's 2, 4, 6, so 1 half is 3. Add up this, and it's 4 minus 5 minus 1, 6 minus 5 plus 1. So the formal charges for carbon is minus 1, for oxygen is plus 1, and you see when you add them up, equals 0, because that's a neutral molecule. That way, you can double check on your work and make sure you didn't make a mistake. What if you have an ion? Okay, well, let's look at this one, and we have 4 chlorines. They're all identical, but I'm going to do each one separate to show you what you're supposed to be doing. But obviously, you don't need to do that iodine, because they all have 1 bond, 6 lone pairs. But let's just do it. Valence electrons, chlorine has 7, 7, 7, 7. Iodine has 7. Right? Now, lone pair electrons, 2, 4, 6. And we have the same thing in all the chlorines. Iodine has 4. 1/2 of the bonding electrons. Each chlorine has 2 bonding electrons, so 1/2 is 1. Iodine has 2, 4, 6, 8, so 1/2 is 4. 7 minus 6 minus 1 is 0, 0, 0, 0. So the formal charges of the chlorines are 0. Iodine is 7 minus 8 minus 1. Iodine is minus 1. Again, to make sure you're right, you add up all of these numbers, comes out to minus 1. The charge of the ion is minus 1. So you know you're right. Okay? This is not difficult. Just go slowly. Don't forget only half of the bonding electrons. You have another example in here. Okay, so we have 3 chlorines. Once again, they're identical. You don't need to do each one individually. Just like to do it when I'm teaching, okay? Valence electrons. Chlorine has 7. Bromine is also halogen, so it has 7. Lone pair electrons. Each chlorine has 6. Bromine has 4. 1/2 of the bonding electrons. Each chlorine has 2 bonding electrons, so 1/2 is 1. Bromine has 2, 4, 6, so 1/2 is 3. So you add up the numbers, 7 minus 7 is 0, 0, 0, 7 minus 7, 0. They all have 0 as a formal charge. So of course if you add them up, equals 0, that's a neutron molecule, so you know you're right. This is not hard at all, although it doesn't hurt to practice. So how do we use them to tell which one is the most favored, the most stable, the most likely resonance form? These are the rules. When all formal charges are 0, that's preferable. That's your first choice. Okay? If you can have one resonance form that all the formal charges are 0, that is the best. Now, if they're not all 0, then the next best would be the smallest non-zero. But sometimes you can have non-zeros, they're all the same numbers, but they're two different formal charges. So in that case, you want the negative formal charges to be on the most electronegative atom. And how do you know the most electronegative? You look at the periodic table. Remember, electronegativity increases from left to right, decreases from top to bottom, because fluorine is the most electronegative. You already know that. Okay, so let's do some examples. I have already calculated the formal charges in here. So this is carbon dioxide. You have 3 different resonance forms in there. Which one is the best? This one, because it's all zeros. We said that's the preferred. So wasn't that easy? That is the preferred molecular structure. Okay, that's the nitrogen monoxide. None of them are all zeros. Well, I can eliminate this one because that's the biggest number. We want the smallest possible numbers. And keep in mind, the sign does not affect this. We're just saying that 1 is less than 2 and 0 is less than 1. We don't include a sign for that one. So since you have a 2 in here, we can eliminate this one. So we have one resonance form that has a -1, a +1, and a 0. The other one has a 0, +1, -1. They look exactly the same. So what did the third rule say? Find the negative formal charges and see in which atom. This one is on the nitrogen. This one is on the oxygen. If you look at the periodic table, oxygen is more electronegative. So this is the preferred form. This is not complicated. Once again, practice makes perfect. So if you want to work one-on-one with me, if you want to get one of my worksheets to practice, there's a link to my Wyzant account in the video description. Make an appointment and I'll be glad to work with you.